A 100% local AI stack means exactly what it says: zero client data, zero prompts, zero embeddings, and absolutely no telemetry or logs transmitted to third-party infrastructure. For most businesses, this is a privacy preference, but for highly regulated industries handling sensitive data, this strict isolation is a non-negotiable baseline. Under the HIPAA security rule enforced by Health and Human Services, organizations must implement administrative, physical, and technical safeguards to protect electronic protected health information. Similarly, attorneys operate under strict ethical bounds. Under American Bar Association Model Rule 1.6, lawyers have an ongoing, mandatory duty of confidentiality to safeguard client information against unauthorized access. Deploying a true air-gapped AI architecture fulfills a mandatory legal obligation to protect against professional liability and regulatory sanctions. The challenge of bringing AI in-house has shifted. Raw hardware compute capability is no longer the bottleneck for local inference. Modern isolated server racks possess enough sheer processing power to run state-of-the-art multimodal workloads entirely off the grid. The actual barrier is integration. You have to weave together true open-source software, heavily restricted open-weight models, and rigorous legal compliance into a single unified system. To do that, we have to engineer a precise reference architecture for a fully local AI platform, building it out layer by layer. The objective is an enterprise-grade AI supercomputer engineered for deterministic, secure reasoning. The first step in building this stack requires clearing up a pervasive misconception. In enterprise AI, open source rarely means what you think it means. The software infrastructure, the databases, orchestrators, and inference servers, operates under true open source initiative-approved licenses, like Apache 2.0 or MIT. As this diagram illustrates, AI models themselves sit in a different category. The actual weights, training code, and datasets are overwhelmingly open weight, not open source. Many popular models carry field of use restrictions under licenses like OpenRail, which explicitly disqualify them from the OSI definition. Because of this split, selecting a model for a regulated enterprise requires intense scrutiny. It is a legal procurement task wrapped in an engineering decision. With the licensing reality established, we start at the base of our architecture. Layer 1, the bare metal hardware and compute layer. A single workstation GPU might have enough VRAM for one user running a quantized model, but serving multiple enterprise users simultaneously quickly exhausts memory bandwidth and capacity. To scale, you need the enterprise cluster tier, engineered specifically for massive VRAM pools and multi-terabyte per second memory bandwidth. State-of-the-art inference relies on tightly packed arrays, like servers configuring 8 interconnected NVIDIA H100 GPUs. Alternatively, architectures like AMD's MI300X push hardware limits through high-capacity HBM3 memory, delivering 192 gigabytes per accelerator to hold massive models in active memory. To manage this power across dozens of staff, operators use multi-instance GPU, or MIG, to slice these massive cards into smaller, isolated hardware instances. MIG is an operational necessity. Physically partitioning the compute prevents cross-tenant data interference, ensuring a batch job in the billing department never touches the hardware lanes processing confidential legal or medical texts. Moving up the stack, Layer 2 manages the software supply chain inside your locked-down, air-gapped building. The standard open-source orchestrator for managing these containerized applications across multiple hosts is Kubernetes. Because this cluster has zero internet access, it requires a private, offline artifact registry, like Harbor, to store these application containers safely. As this pipeline shows, every unverified code package entering the isolated network must be systematically scanned for vulnerabilities, cryptographically signed, and locked into the secure registry. Open-source tools like Trivy and Cosign handle this continuous scanning and signing process locally. Executing this rigid offline supply chain directly satisfies HIPAA's required administrative safeguards for ongoing risk analysis and vulnerability management. Next are layers 3 and 4, constructing the data plane and the semantic memory systems that feed proprietary information to the model. The ingestion phase requires storing raw internal documents locally, then running optical character recognition to extract the text and metadata. High-quality answers require a dual-path hybrid retrieval system. The query splits into a full-text keyword search and a semantic vector search. These tracks merge into a re-ranking filter, discarding irrelevant results before passing the most precise data upward. When parsing thousands of pages of legal discovery or navigating complex medical records, the retrieval mechanism dictates the system's ultimate performance floor. A highly tuned local retrieval plane mathematically guarantees the model only analyzes what the user is explicitly permitted to see. This establishes the technical foundation for HIPAA's minimum necessary access standard. Finally, we cap the architecture with Layer 5, the inference engine, where the large language models actually run. You need a high-throughput inference server like open-source VLLM to manage prompt flow and memory caching efficiently. The critical boundary constraint here is strict isolation. The inference server operates entirely behind an internal API that never touches the outside internet. The final user interface layer connects exclusively to this internal API, providing staff with safe access to internal chat and automation workflows. This completes a fully sealed 5-layer ecosystem. It protects data sovereignty down to the silicon while delivering precise generative capabilities. With the system architecture complete, the focus shifts to user execution, how professionals actually interact with this local stack. Treating a language model as an absolute truth engine is a massive liability. Safe operation requires the bounded assistance framework, which imposes hard limits on what the AI can claim. Under this framework, the AI functions strictly as a reasoning and drafting layer, forcing its answers to be completely grounded in the internal documents fed to it by the retrieval system. Operationally, the AI must provide exact citations to those retrieved text snippets, and the system must maintain a permanent audit trail tracking who queried what data. Courts have already issued harsh professional sanctions against attorneys for filing briefs padded with hallucinated, non-existent case citations generated by unconstrained AI tools. Bounded assistance is the structural cure to the hallucination problem. It forces the AI to objectively prove its work before a professional can rely on it. Even with these guardrails, this fully air-gapped stack delivers immense practical utility. It easily handles private internal chat, large-scale summarization of massive discovery sets, and offline transcription of sensitive audio. But there are structural limits. You cannot simply download and natively ingest proprietary legal research databases due to heavy editorial copyright restrictions. Despite those limits, this exact architecture directly answers the rigid regulatory frameworks we started with. The stack's role-based access controls and metadata filtering explicitly fulfill the HIPAA mandate, mathematically restricting access to the minimum necessary patient information. And the offline supply chain, paired with strict bounded inference, fulfills the American Bar Association's ethical requirements for technological competence and absolute client confidentiality. Buying a disconnected server rack does not automatically make an organization compliant. True enterprise compliance is achieved only when a multi-layered technical architecture enforces strict, auditable governance over the AI.